Okay, so we've got a couple of charges, assuming they're both positive, they're going to both repel each other. So charge 1 experiences a force to the left from charge 2, and charge 2 experiences a force to the right from charge 1. And what should we assume about the strength of those forces, the magnitude, now that we have the directions? Yeah, they should be the same magnitude. This is Newton's third law, that the two objects interacting with each other exert equal and opposite forces on each other. So the force of object 2 on object 1 and the force of object 1 on object 2, same amount of force, just in opposite directions. In fact, I think it's useful to think of these as the same force, just looked at from two different perspectives. And because of that, we don't really need to consider both of these forces. We can look at just one of these forces, and then we know the other one's going to be the exact same amount, but opposite direction anyway. And in many cases, when we're dealing with electrical forces, there's typically one object that we care about, like one object that we want to figure out the forces on that object. And everything else we're just treating as something causing an effect on that object. And the usual terminology we use for that, let's say we care about the forces on this object on the right. We usually call that the test object or test charge. And then any other charged object or objects that are creating that effect, we typically call the source charge. So let's assume we have a charge we're calling the source charge and another charge we're calling the test object. And there's no physical difference between these. There's just two charges that are exerting forces on each other. But the idea here is we're treating this as an object we're calling the source charge creating some sort of effect that's felt by the object we're calling the test object or test charge. So the source charge is creating some sort of effect, and the test charge is feeling a force from that effect. And this is completely reversible. We could think of the right object as the source charge and the left object as the test object, because they're both exerting forces on each other. But let's say we only care about the force on the test object. Maybe the source charge is being held in place, or maybe it's so massive it's hardly going to move, or maybe we just don't care about its motion. But that's what we mean by when we say test object. The test object is the object where we care about the forces acting on it. Any questions on that terminology so far? And let's throw in some numbers here. Let's say this source charge is just some absolutely enormous charged object, some charged object with a very large amount of charge. And this test object, let's say we know the charge of it. Let's say this test object has charge positive 6 coulombs. So positive 6 coulombs, and let's say we place it here and we measure the force acting on it. And we find that that force happens to be, let's say, 24 newtons to the right. So a 6 coulomb object experiences a force 24 newtons to the right. And let's say we now replace that 6 coulomb object with a different object. Let's say we put a new object here that's, let's say, a stronger charge. Let's say we replace this with an 18 coulomb object. How much force would you expect that 18 coulomb object to feel instead of these 24 newtons? It's still positive, so presumably it will still be repelled by the source charge.
72.
But would you expect that to be same force or stronger or weaker?
Stronger, 72.
Yeah, and why 72 newtons in particular?
Because the charge of the second one is 3 times bigger than the first one, so the force is 3 times bigger.
Yeah, with everything else being the same, I mean, we're putting this in the same situation. it's 3 times as much charge, so we should expect it to experience 3 times as much force. Or alternatively, what if we put in a charge in the same location, assuming that we're just removing the charge we've already got and putting a different charge there. Let's say we put in a charge whose strength is, let's say negative 3 coulombs. First of all, what would be the direction on the force here, or direction of the force on this object?
To the left.
Yeah, going to be to the left. And how strong compared to the original? Yeah, it's going to be attracted to the source charge. And based on the charge here, what would you expect the force on it to be?
12.
What was that?
12.
Yeah, 12 newtons, because why?
It's half, the charge is half the original.
Yeah, it's half of the original 6 coulomb charge, so we should expect it to have half as strong of a force. So these particles are all experiencing different amounts of force because they all have different amounts of charge. But these seem to be proportional. We expect, and this turns out to be correct, we expect that the force is proportional to the charge. Force is proportional to test charge. Test charge usually being written as lowercase q. So force is proportional to charge. That suggests that force equals something times charge. Because if two quantities are proportional, that just means we can write one of them as equal to some constant times the other. So there's got to be some multiplier, some constant that we can multiply by each of these charged objects to figure out the force on that charged object. And we call that multiplier E, the electric field. So E could be thought of as the quantity we multiply by Q, the charge, to figure out the force on the test object. And in this case, what is that multiplier? What do you multiply each of these charges by to get the force acting on it?
Can you repeat the question?
In this case, there's got to be some multiplier that we multiply by each charge to figure out the force acting on it. And we can actually find that. If you isolate E here, what would you get?
Force divided by Q.
Yeah, force divided by charge, F over Q. So you could think of this as a definition of the electric field. What electric field means, what this quantity E means, is the ratio of force over charge. That is the ratio of the force that is felt by the test object divided by the charge of the test object. So if we calculate these for each one of these, force over charge, force divided by charge, 24 over 6 would be how much?
4.
And what would the units be for that? For what?
Newton over C, coulomb.
Yeah, exactly, newtons over coulombs, newtons per coulomb. So we can say the electric field is 4 newtons per coulomb. And then for this one, force over charge, that's 72 newtons over 18 coulombs, that's also 4. And this one, force over charge, would be 12 newtons over 3 coulombs, that's also 4. We've got to be careful about directionality though, because force is a vector and charge is a scalar. If you take a vector divided by a scalar, would the result be another vector or another scalar?
Another vector.
Right. So we should treat electric field as a vector. So if you think of force as a vector, electric field also has to be a vector, specifically because it can be multiplied by a scalar to get another vector. So electric field is a vector quantity that's equal to force as a vector divided by charge. And generally, if you take a vector and multiply or divide by a scalar, what happens to the direction?
If the scalar is negative, and it would change the direction of the force. And
Right.
If it's positive, then it's the same.
Exactly. So for any positive charge, the electric field vector and the force vector are in the same direction for a positive test charge. So that means the electric field vector is 4 newtons per coulomb to the right. For instance, 24 newtons to the right divided by 6 coulombs is 4 newtons per coulomb to the right. 72 newtons to the right divided by 18 coulombs is also 4 newtons per coulomb to the right. Even for this one, if we've got 12 newtons to the left and divide by -3 coulombs, what do we get?
We get to the right.
Yeah, 4 newtons per coulomb to the right. So the electric field is 4 newtons per coulomb to the right for all of these. Because even though they're experiencing different forces because they have different charges, this ratio of force over charge is the same ratio for all of them. And that ratio is what electric field is, what electric field means. So that's really all electric field is. Electric field is this ratio of force over charge, the force that would be felt by a test object divided by the charge of that test object. And the thing is, since this electric field is the same no matter what charge we put here, we can say the electric field isn't really a property of the test charge. The electric field is a property of this location in space. So even if we don't put any test objects here at all, even if this is just an empty point in space, we can say this point in space has an electric field of 4 newtons per coulomb to the right. So you could think of this electric field as representing the capability of this point in space to exert a force on any test charge that we might choose to put there. If we were to put a test charge in this location, it would experience a force equal to 4 newtons per coulomb times the charge of that test object. But even if we don't put a charge here, even if this is just an empty point in space, we would say this location has an electric field equal to 4 newtons per coulomb to the right. Any questions on that so far?
So if it's the same source charge throughout the problem, then the electric field anywhere will be a constant. Depends on what kind, or if you put like a force, a test charge there, then it will depends on the test charge that the force of the electric field affect on that test charge, right?
Well, different test charges will experience different forces, but the electric field will be the same no matter what test charge you put there. So force is a property that depends on what test charge you're using. But electric field is a property of this location in space, whether there's a test charge there or not.
Thank you.
For example, if we were to put a different test charge here, let's say we put a test charge of, let's say 100 newton or 100 coulombs. In that case, what would the force be?
400.
Right. We have a force on this particle of 400 newtons to the right. So the force depends on that test object. But the electric field, the ratio of force over charge, that's a property of the location in space. It does not change based on what test charge we're using. It's ultimately caused by the source charge, but we can treat that electric field as a property of the location in space, regardless of what test charge we put there, or even whether or not there even is a test charge there. And this is ultimately why we call it a field. A field just means a function that has a value at each location in space. And in fact, it depends on the location in space because, for instance, let's say we take this test charge and move it closer to the source charge. If we move this object closer to the source charge, what would you expect to happen to the force?
It will increase.
Sorry, what was that?
It's increase.
Yeah, it's going to increase. Moving closer to the source means we get a stronger force. The force is stronger, but if we calculate electric field, the stronger force divided by the same test charge results in a stronger electric field vector. So the electric field value does depend on location. The closer you are to the source charge, the stronger the electric field will be. So what that's going to look like, if we were to map out the electric field, because any field we can actually map out, if you're close to the source charge, we should expect a very strong electric field. If you're further, the electric field is going to be weaker and weaker and weaker. And in terms of directionality, what if we were, let's say, above the source charge? which direction would the electric field point?
Upwards.
Right, upwards. Because if we were to if you hypothetically put a test charge here, and also to get the direction right, it's a good idea to visualize a small positive test charge, because the electric field is the force that would be experienced by what would be the easiest Q to divide by, the easiest value of Q?
Q1.
Yeah, if you imagine Q is exactly 1 coulomb, F divided by 1 is still just the same number as F. So you could think of the electric field as the force that would be felt by a 1 coulomb test charge. So if you're not sure what the electric field is at some location, imagine you're putting a positive 1 coulomb test charge at that location and visualize what the force would be. At this location, directly above the source charge, a positive 1 coulomb test charge would get shoved upwards by repulsion. So above the positive source charge, we get an upwards electric field. Likewise, if we're above and to the right, we're still going to get repelled. If you had a positive test charge, you're still going to get repelled away. And then getting weaker as you get further away. In fact, no matter where you are, which direction should we expect the electric field to be?
Outwards.
Yeah,
away.
Outwards from this source charge. Yeah, pointing away. And then getting weaker as you get further away. So that's what we should expect the electric field to look like near this positive source charge. Yeah, exactly. If we had a negative test charge, or not a negative test charge, a negative source charge. Because remember, the electric field is a property of the location. It does not depend on what test charge we put in, or even whether there's a test charge at all. The electric field depends only on the location, and yes, the source charge. If we were to make this a negative source charge instead, like let's say we have, if we make this source charge negative, make this a little smaller. In that case, if we imagine a small positive test charge, let's say over here you put in a small positive test charge. And we're assuming positive here just because of how we define electric field. That small positive test charge is going to get pushed or pulled in which direction?
Inwards.
Yeah, which means the electric field should be pointing inwards, because electric field, again, could be thought of as the direction a small positive test charge gets pulled or pushed. So inwards, and that's true from any direction. Electric field is going to be pointing towards negative source charges and away from positive source charges. And again, that's going to be strong if you're nearby and getting weaker as you get further away. So we should expect the electric field to look something like this if you're near a negative source charge. Any questions on that so far? And also, one other convenient way to draw this out, if you draw out the electric field by mapping out these individual arrows, it ends up being kind of inconvenient. You have to draw in all these little arrows, which gets really tedious, and the diagram gets really cluttered and kind of difficult to read. So often what we do instead is what's called a field line diagram. The field line diagram, the idea is instead of drawing out all the individual arrows, you just draw sort of lines representing the general trend. Like all of these are just arrows pointing straight inwards. So if we just draw out, instead of individual arrows, if we just draw out rays or lines representing the overall trend, like all of these are just linear directions pointing straight inwards towards the source charge. So if we just draw in something like this, just a line with an arrowhead on it showing directionality. Something like this. This conveys pretty much the same information. And we want these to be evenly spaced because we don't want to indicate any sort of bias in one direction or the other. So this would be the idea of a field line diagram, not drawing out the individual arrows, but just showing the overall trend in directions. Any questions on that so far? And note that this conveys pretty much the same information in terms of everything's going towards all of the electric field values are going towards the source charge if it's negative, or away if it's positive. We should probably label this. This represents the electric field. What information do we kind of lose there, though? What information do the arrows convey that these field lines don't?
Magnitude?
Right. The field lines pretty clearly show the direction, but you kind of lose information about magnitude. These don't show the size of the electric field in the way that the arrows do. But we still kind of have the information based on what? How does the field line diagram like this convey some information about magnitude?
The distance between in between a few lines.
Right. How close or how far those field lines are. Like if you take a look at a region, like let's say the region very close to the source charge, notice that the field lines are kind of close together. Whereas further out, the field lines are much further apart. So how can we interpret that? If the field lines are very close together, what does that suggest?
Stronger force?
Yeah, or I wouldn't say a stronger force, because this isn't mapping forces, this is mapping the electric field. But we could certainly say a stronger electric field. And likewise, when we're further away, it looks like the field lines are more spaced out. There's more space between them. So we'd say that's a weaker electric field. So even though the electric field lines don't directly show the magnitude that arrows with sizes do, we can still interpret this as if the field lines are close together, that suggests a stronger electric field in that region. If the field lines are further apart, that suggests a weaker electric field in that region. Any questions on that so far? Then let's see what would happen if we have more than just one charge. Let's say we have a situation with, do you want to try 2 positive charges or 2 negative charges or one of each? Sure, let's try one of each. Let's say you've got a positive charge here and a negative charge here. So a positive test charge and a negative test charge. Something like that. And let's say they're fairly spaced out. Something like that. And we want to draw in the electric field that these create. Because the idea is each one of these source charges, if we treat these both as source charges, the source charge or source charges create this electric field in the space around them. And once you know the electric field, you can say that electric field creates a force on the test object. So that's the general scheme here. These source charges create electric field in the region around them. And then the electric field creates a force on the test object. So we're kind of thinking this is a two-step process. The source charge creates an electric field, and the electric field creates a force on the test object. And of course, what's really going on is the charges are exerting forces on each other. But it's useful to think of it as the source charge creating this invisible phenomena called the electric field, which creates a force on the test object, because then we can split it up. You can deal with the source charge creating an electric field and figure out how to draw that. And once you know the electric field, you can say the electric field itself creates a force on a test object, and you could ignore the source charge entirely. So ignoring the idea of the force so far, let's say we're just looking at the source charges creating an electric field. What we can do here is we can look at the electric field that would be created by each source charge individually and then combine those together. For example, let's say we're talking about a location in between. Let me label these. Let's call these charge A and charge B. If we're in the in-between zone, like let's say exactly in the middle, charge A creates electric field in which direction?
Outwards.
Which would be left, right, up, down?
Right.
Yeah, charge A creates electric field to the right. And what about charge B? At this location in the middle, charge B creates electric field in which direction?
Also to the right.
Yeah, should be also to the right. Because charge B is a negative charge, so electric field should point towards charge B. In fact, it might be useful to draw, just as a reminder, electric field going outwards from the positive charge. Just little arrows all around it. And inwards towards the negative charge. Just as a reminder to yourself. So in the in-between region, outwards from A means to the right, but also inwards towards B also means to the right. So we've got electric field contribution from each one going to the right. And how do we combine those contributions to find the actual electric field in that region? Yeah, exactly, vector addition. And this is generally called the idea of superposition. Superposition basically just means if you've got two or more things acting on the single location, you can add together their effects. And this is very much like the idea of interference with waves. If you've got two sources trying to create waves in the same space, you can add together the wave equations, add together the displacements. Same idea here. We've got two source charges trying to create electric field in one location. So we can calculate the contribution from each charge, each source charge, and add those together as vectors. So a vector to the right plus another vector to the right is just going to be an even bigger vector to the right. So the actual electric field at this location is a strong vector to the right. And that should be true anywhere in the in-between region. In the entire in-between zone, on that one-dimensional region, we're going to have a strong vector to the right. What about on the left side, if we're over to the left of A? If we're on the left side of A creates electric field in which direction?
To the left.
Yeah, to the left, which is away from A. And at that same location, B creates electric field in which direction?
To the right.
To the right. And should that be the same strength or stronger or weaker than the contribution from A?
It's weaker because it's further from B than A.
Exactly. We're further from B and closer to A. So the effect of A should be strong and the effect of B should be weak, assuming A and B have the same amount of charge. So if we've got a strong vector to the left plus a weak vector to the right, what does that tell us about the result?
In between vector to the left.
Yeah, it's going to be to the left, but it'll be an intermediate strength, a weaker strength. So we're going to have a weak vector to the left if we're to the left of A. And the further you get, the weaker that's going to be. So we're going to get very weak vectors to the left when we get further out. And probably still fairly strong if we're still close to A. So if you're very close to A, you're going to get a fairly strong vector to the left, but that gets weaker really fast because B is acting against that. Meanwhile, what if you're on the right side of B? What would the effect on the right side of B look like?
Bigger to the left vector into B, and it's vector with smaller magnitude as it's go further away from B.
Yeah, because you've got a leftward vector, leftward electric field contribution caused by B, and A is causing a weaker contribution to the right. So they partially cancel out, but the overall effect is to the left. So on the right side of B, we get a vector to the left, but that's going to get weaker in a hurry as you get further away. So something like that. So that takes care of pretty much the entire x-axis. Let's take a look at when we're off of that, if we're above or below. And I think we can take advantage of the symmetry here. If we take a look at what's going on above, what's going on below should be an exact mirror image of it, because there should be no real difference between above versus below. So let's say we're at a location maybe directly above, like let's say a location directly above the center point. At that location, A creates electric field in which direction?
Upwards.
Straight upwards? And it shouldn't be straight upwards here. I would only expect straight upwards if we're directly above A.
About to the right a little bit.
Yeah, because we should expect the electric field to be directly away from A. So if you imagine a line emanating outwards from A through that point, yeah, to the northeast or up and to the right or whatever you want to call it, it should be pointing directly outwards from location A or directly away from location A. So along that line through location A. And what about the electric field contribution caused by charge B? Which direction would that be?
Northwest.
Sorry, what was that?
West, but inward. Right?
Yeah, it should be inwards towards location B. So yeah, that'll be southeast or down and to the right, whatever you want to call that one. So straight towards charge B. And assuming we're directly above or below the middle, we're equidistant from A and B. So these are going to be the same strength. And what happens if you add those vectors together? If you add northeast plus southeast and they're the same strength, what's going to happen there? Yeah, it should end up pointing directly to the east. And there are a couple of ways you can think of this visually. One way is if you add these head to tail. So go to the northeast, and then I guess that should be a little larger to make this to scale. So northeast and then southeast, you end up just going straight to the east as the total vector here, the net electric field at this point. You could also think of this in terms of components. If you imagine splitting each one of these into its components, you've got a northwards y component plus a southwards y component. So the north and south y components cancel out. But for the x components, you've got eastwards and more eastwards. So the opposite y components cancel out, but the same direction x components combine. So at this location, the overall electric field is to the east and fairly strong. Any questions on that so far? So we've got electric field at this location directly to the east. And the same logic should apply to directly underneath the center as well. Because like I said, we should expect complete symmetry. If we wanted to make sure we've got away from A plus towards B, again, that's a northeast vector plus a southeast vector adds up to an eastward vector. So directly below the center, the electric field is also due east. And that should really be true anywhere directly above the center or anywhere directly below the center. These are all going to be directly to the east. So anytime you've got electric field on that y-axis, directly above or directly below the center, it's got to be directly to the east. Any questions on those electric field values so far at these various different specific locations? And we've kind of been skimming over the strength of these, but presumably it should be fairly strong when you're close and getting weaker as you get further away. So let me correct for that a little bit. Getting weaker as you get further away, and fairly strong when you're close. So strong when close, and then getting weaker and weaker and weaker. Maybe something like that. And very strong when you're in the in-between zone. But let's try out some more locations. Maybe if you're like, let's say, directly above location A. If you're directly above location A creates electric field in which direction?
Straight upward.
Yeah, straight up or directly to the north, and fairly strong because we're close to it. But also at that same location, B creates electric field in which direction?
Down towards B.
Yeah, downwards and to the right towards B, and presumably weaker because we're kind of far from B, but we're close to A. So you got a northwards contribution from A, and sort of east southeast weaker contribution from B. We add those together, and I think probably just joining them head to tail is going to be easiest here. So our actual electric field would be, if we put them together head to tail, from the start of the original one to the end of the last one. So at this location, the electric field is north-northeast, or up and a little bit to the right. So that would be the electric field at this location. And I think a convenient way to think of this, if you just consider A, we should expect the electric field to be straight up, but the presence of B biases it in the towards B direction. So you could think of this as electric field caused by A would be straight up. The presence of B tilts it in the towards B direction. Similarly, if we had an electric field, let's say directly under A alone would create electric field in which direction? If you were directly below location A, charge A on its own would create electric field in which direction?
Did you ask us a question? Can you repeat it?
Yeah, if you're at a location directly south of A, what would be the electric field caused by just charge A at that location? Yeah, it should be directly to the south. But charge B biases that because charge B being negative biases all electric field towards itself. So instead of being straight to the south, this is going to be to the south and a little bit north and east. So it gets tilted to become this diagonal instead. And we can do the same thing for anything near B. Like directly north of B, we should expect electric field straight towards B. But charge A biases that by pushing outwards. So the positive charge of A pushes that a little bit outwards. Likewise, if we're directly to the south of B, we would expect electric field straight towards B. But again, A being positive biases it a little bit outwards, pushes it away from A. So I think this is a very useful way of thinking about this. If you're dealing with several charges, conceptually, you can think of it as at some location, what would be the electric field caused by just the nearest charge? But then bias that by pushing it away or away any other positive charge or towards any other negative charge. So we can map out individual locations, but presumably what we really care about, what we really want to draw is the electric field lines. And for that, I find it very useful to imagine some specific number of arrows or curves coming out of each charged object. I would usually start with, let's say, either 4 or 8. You want to be consistent about it is the important thing. So let's say we've got 8 arrows coming out of each location. Or 8 arrows coming out of the positive charge. And we've got to also have 8 arrows going into the negative charge. for consistency. And if you think about how each one of those is going, presumably in the in-between, it's just going straight to the right and very strong. And also on the left side, going straight out forever, but fairly weak. On the right side, going straight to the left, inwards, and fairly weak. And keep in mind, we're going to represent the strength or weakness based on density of the field line. So we'll get to that afterwards. But also, if you look at this in terms of the, like I was saying, the being biased by the other one. Like for instance, let's say we look at the curve going upwards from source charge A. If it were just the positive charge and that's it, we'd expect this to just go straight up. But instead that gets biased, being pulled towards charge B. So instead of going straight up, it's going to go up, but curve around. And as we found earlier, it's got to be going straight to the east as it passes through the center. And presumably it's going to curve inwards towards the negative source charge. So we should expect this curve to look like this. And by symmetry, same thing underneath. Going directly south away from the positive charge, but curving because of the bias from the negative source charge, becoming flat as it passes through the center, should be flat, and then back inwards towards the negative source charge. Any questions on those curves so far? And then we can fill in the others, like this one this diagonal would go straight to the northeast forever if it was just the positive charge. But instead it gets biased as bending towards the negative charge, flattening out and then going inwards. So something like this. And likewise underneath, this one would go southeast forever, except it gets pulled in towards the negative source charge. And note that in this interior region, we get field lines fairly close together. What does that suggest? If the field lines are packed close together.
Stronger charge?
Right. And that's exactly what we should expect. In this in-between region, everything's pulling to the right or pushing to the right. So we should expect a strong combined electric field there. Whereas in the outer regions, for instance, this one going to the northwest, gets sort of gradually pulled in towards the negative charge, curving around, becoming flat, and then curving back around to here. And likewise, the same effect underneath, completely symmetrical. And note that these field lines are more spread out. Like in this region over here, for instance, these field lines are very far apart. So that suggests a very weak electric field. Whereas let's say in this zone, the electric field lines are much closer together, suggesting a much stronger electric field. So this is the electric field we expect, sort of emanating outwards from the positive source charge, curving around as needed to go inwards towards the negative source charge. This is the typical electric field shape we get anytime we got two opposite charges, a positive charge and a negative charge acting as these source charges. And then at any location, like let's say we care about this location here, suppose we put a test charge there, let's say a small positive test charge. If we've got a little positive test charge here, what direction would the force on that test charge be? Based on the electric field we know here.
Along that circular line?
Yeah, along that curve, along that field line. Because the electric field at this location is kind of north-northeast. So the force on a positive test charge will be the same direction as the electric field, north-northeast. So you can use the electric field line diagram as sort of a map of the electric field everywhere. And any test charge you place at some location will experience a force in the direction of the electric field if the test charge is positive, or in the direction exactly opposite to the electric field at that place if it's a negative test charge. So that's ultimately what this field line diagram is. It's a map showing the electric field everywhere in space. And we should expect those field lines to be emanating outwards from any positive source or going inwards towards any negative source. Any other questions on that?
Can you quickly draw the field line of the two same charge?
I don't think we're going to have time for that, but try it out on your own using the same technique here. And keep in mind, it's always going outwards from a positive charge or inwards towards a negative charge. Try mapping it out one location at a time to get the general trend, and then try drawing in the field line curves. So try that out on your own, and we can take a look at the examples of that next time as well. And you can also look that up online. Try drawing it out yourself first, but then once you've got an idea of what it should look like, try looking up electric field from two positive charges or electric field from two negative charges, and compare the results shown on the examples to what you've drawn. But definitely try drawing it out first to get some practice. Let me know if you have any other questions beyond that, and I will see you next time.
Thank you.
You're welcome.